Yay!
Yay! Okay, let's talk about magnetic forces, looking at how magnetic fields affect point charges in motion. So this might be the simplest example. So suppose I have a point charge here, and by the way, this is a positive point charge Q, right? So here's Q, and what's going to happen is that Q is going to enter this region, and in this region I've got a magnetic field pointed into the page. All right, so there's the B pointed into the page, and then initially the particle has a velocity that's going to be up. So the rule is, how you compute magnetic forces is that it's Q times V cross B, right? It's a little bit like the old idea where, remember, the electric force, the force on a charge due to the electric field it looked a lot easier. It was just charge times the field, right? It pointed in the same direction as the field if the charge was positive. Here, it's the charge times the field, but it's got to be a moving charge. So that's where that V comes from, and then it's pointed in that crazy direction, the cross product. Okay, so if the charge is moving up and the field is into the page, do your favorite right-hand rule, and what you're going to find out is that the force is then directed this way. So here's the force on the charge at that point. This is still all positive charges. And because of the cross product, remember what the cross product does is it ensures that the cross product is the result of the cross product is perpendicular to both of those vectors. So in other words, the force is guaranteed to be perpendicular to both the magnetic field and the velocity. So what happens when you have a force that's perpendicular to the velocity from physics 1, you have circular motion. It's called centripetal motion, right? Just like motion in a gravitational field and something in orbit, the gravitational force is always directed at the planet, perpendicular to the velocity. The velocity is tangent to the orbit. So that's what we've got here. If you do the same thing where the charge is over here on this side, what you're going to find out is that the force is directed, whoops, that's a terrible line. The force is directed this way, again, towards the center. So sure enough, it's circular motion, and then what happens is that the particle is going to exit the field somewhere down here. And if the force is perpendicular to the velocity, remember what that means also is that it doesn't add anything to the speed. It can't, right? If you kick a ball perpendicular to the direction it's moving, all you're going to do is change its direction. There's no component of the force behind it or in front of it that's going to speed it up or slow it down. So the speed doesn't change. It's going to be the same V coming out as going in. It's just the direction is going to be changed. So the particle is just going to bend around. Moving charged particles bend their direction in magnetic fields. Okay, let's see how much. So if this really is centripetal motion, let's use our Newton's laws. So this means if we say the only force that's acting on, let's forget about gravity because we said that was really weak. The only force that's acting on the particle is the magnetic force, and it's QV cross B. All right. So this is the same thing as QVB sine theta, where theta is the angle between V and B. Well, look here. B is into the page, and V is in the plane of the page, and so that angle is going to be 90 degrees. So sine of 90 degrees is just 1. So for this example, the force, the magnitude of the force is just going to be QVB, right? So this has to be equal to the magnitude of the centripetal force, right? That is the centripetal force. So this is just going to be equal to mv squared over r. So we can figure out what the radius of this circular motion is. I can just solve for r. So r is just going to be m, one of those v's cancel, over qb. There we go. We're done. So here's how you would figure out what the radius of the how big of a circle the thing travels in, you'd figure it out this way. Let's look at an example. Suppose this thing were, let's just say it's a proton. So if m is the mass of a proton, so Q is just E, just the charge, the fundamental charge of the proton. Let's say that the magnetic field, just to make the numbers easy, let's say it's 1 Tesla. So it's a nice strong magnetic field. And let's say that the speed is 10 to the 6th meters per second, a million meters per second. That sounds really fast. It turns out for a tiny elementary particle, that's not really fast at all. That's not hard to do. Okay, so let's put these numbers in and see what we get. So R is going to be 1.67 times 10 to the minus 27. V is 10 to the 6th. And then this is 1.6 times 10 to the minus 19th. And B is 1 Tesla. I mean, can we just roughly figure out what the R is? Let's not worry too much about vectors like that. So I'm just going to cancel them because I can. My video, right? My rules. So I'm just going to cancel those. They're pretty much 1. So I just got powers of 10. So on the numerator, I got 10 to the minus 27, 10 to the 6. That's 10 to the minus 21. 10 to the minus 19 on the bottom. So this is just 10 to the minus 2. So that's just 1 centimeter. So is that visible? Can we actually see this kind of a motion? Yeah, you bet. So 1 centimeter, that's certainly something that you could do in an experiment. No problem. Here's something interesting you can do. If it's just a proton, that's just a hydrogen 1. That's just a hydrogen nucleus, right? You might know that hydrogen comes in different isotopes, different numbers of neutrons. There's also something called 2H. That's called, the nickname is deuterium. So that's just a hydrogen with a neutron. That's a stable thing that you find. It's 1 in, I don't remember, 1 in 5,000, 1 in 10,000. Hydrogen atoms in water is actually deuterium. It's a different type. It's not radioactive or anything. It's stable. But anyway, it's just a proton and a neutron. So suppose that some of these were mixed in. Just like in normal hydrogen, if you strip the electron off, some of the nuclei are going to be just protons, and a tiny fraction of them are going to be protons plus neutrons. So if you send all these things in, look what happens. They're different masses, right? It's the same charge. They both have 1 proton's worth of charge, but they have different masses. And so they're going to separate. This thing is going to separate them out because they're going to go in different circles. The one that's heavier, just think about it for a second. What should happen? The one that's heavier is harder to bend around in a circle, right? A bowling ball is harder to bend in a circle than a ping pong ball. So I would expect the radius to be greater for the deuterium. And sure enough, if it's got the same Q in the bottom, but twice the M, neutrons and protons weigh about the same thing. So this is going to be about 2 centimeters. So what this means is something really interesting. Isotopes differ by about 1 centimeter in radius. You know, if you fire them with this particular speed. But anyway, the idea is that this hydrogen will have a certain radius, and some other isotope is going to have a different radius. And so you separate these things out, and you can detect where it is they hit the x-axis again. Maybe you have a detecting plate or something that can absorb the charges. And what you do is you just plot how many hits do you get at these different points. And you might have a lot of them here and just a little bit here if it's an isotope that's not very plentiful. And what you build up is a sort of a sequence of these spikes, and this is called a spectrum. And this is a spectrum that's separated out according to mass. And so this is called a mass spectrometer. Very cool. So you send in some unknown, some sample with a bunch of unknown isotopes, and this thing separates them out by mass, so you can tell what was in your original sample. Very, very cool. The difficulty in this is right there in the V. How do you know what that V is? Because if you know the V precisely, then you're going to have nice sharp spikes, right? The R is going to be well defined. But if the V changes a little bit, or if the V isn't quite certain, then that R is going to be spread out a little bit. If they're not all coming in with the same V, then their R's are going to be spread out. And then some of those peaks can sort of run together and you don't get good resolution. So what you do, because measuring the speed of these things is actually a little bit tough. What normally happens, how do you get something to go, how do you get a charged particle to go a speed v? What you do is you accelerate it through a voltage, right? Maybe you have some plates down here, maybe there's a plate with a hole in it, and so you have a negative and a positive, and so you accelerate these things through some voltage, delta v. And then you have a little hole in the plate, and then you make a little beam of these things. So what you can do is you can, instead of having this in terms of a speed that you don't really know what that is, you do know, because you presumably built the device, you know what that potential difference is. So we can write it in terms of the potential difference. Remember in some previous video, we talked about accelerating a charge through a voltage. And so if 1/2 mv squared, if the final kinetic energy of these things is just the energy of the voltage they're accelerated through, E delta V, that's just kinetic equals potential, then I can solve for the V, right? Well, which V? The velocity. We got to be careful because those V's kind of look the same. So if I solve this, this is going to be V is the square root of what? 2E delta voltage over m. And then I can plug that into my radius equation up there, and now I can get it in terms of things that I know, which is like the potential difference that I accelerate these charges through. So this means that my R, if you were really going to do this experiment, you might do R as, what would that be? M over QB times, actually, oh, let's just call it Q, that's fine. So this would be 2Q delta V over M. So if I were going to combine all of this together under the square root, I might say it's 2, the Q is going to fall to the bottom, right? The M is going to be up top, and so this is going to be M delta V over QB squared. Looks like that's what I'll get finally. And so here we can solve for where we would expect these things to show up, at what radius, just based on their mass, their charge, and then the potential difference we accelerate them through. And one experiment that we do, I know when I'm doing my classes, is that we can use this to measure extremely small masses. Because you might wonder, when you look at a periodic table, how is it we know the masses of these tiny nuclei? You can't just put them on a scale, right? Because we're measuring things that are like 10 to the minus 27 kilograms. How do we measure? How do we get so many decimal places? How do we know the mass of the electron? For heaven's sake, that's 2,000 times less. The answer is, this is what we do. We send them through magnetic fields and watch how they bend. So one classic lab experiment you can do is, suppose these are not protons, but suppose they're electrons. You just fire electrons into a magnetic field, accelerating them through some voltage, and you look at the circle. You look at the circular motion, and you can derive what the mass of the electron is. So this is a fancy way to weigh things. And not only a fancy way to weigh things, but also a fancy way to separate isotopes. And one of the uses of a mass spectrometer is to radioactively date things. There's a couple important things you might have heard of, like carbon dating, right? There's regular carbon-12, and then there's radioactive carbon-14. And you might want to know in some sample what's the ratio of these two, because that tells you in a pretty straightforward way how old the sample is, at least when it was last alive, because you do this on organic samples, things that used to be alive, like bone or wood or whatever. So what you do is you take a little sample and send it through this mass spectrometer. You ionize it, you take away the electrons, and what's nice is that the carbon-12 and carbon-14, it's the same amount of energy to ionize the electrons, to take one electron away from both, roughly. So you separate these things out by mass, and then the mass spectrometer tells you what the ratio is. And so this is very useful in doing all sorts of different dating. And this can also be used for not just carbon dating, of course, but for any sample. So we can do radiometric dating of rocks with uranium to lead, or any of the other date markers that we have. So this is an extremely valuable technique.